Good morning. Come on, you're going there. Come on, good morning. Good. Now you're awake. Because it's afternoon nap. You're waking up. Time to go. So I am not a software developer, but I develop software. I'm a researcher, and I mostly develop programming languages, often in a day or an afternoon, and I throw them away. This morning, somebody said, you might be afraid of throwing away code, but no, I throw away entire programming languages because they're that cheap to produce. And that's the point that I want to make today. What I want to talk about first is why in the world you would think about this, because if you go to an academic conference on programming languages, for example, International Conference of Functional Programming, what you often see is talks on verification. More verification, yet more verification. And you won't believe it, the fourth talk and the last one will still be on verification. Well, you are at a developer conference, so you see slightly different topics that are a bit older. Monads date back to the late mid-'80s, when Marchi invented or brought them over to computer science, type classes. A little bit later, were repopularized by Wardler, for example, GADTs, and verification again, right? Because this morning we need to have correct software. I actually don't believe that that is the big problem of software development. I honestly believe that programming language people focus on verification because it's the easier problem. What the real problem is that you, if you are developing, that you're facing out in development land, is the incredible complexity of software, and you're always willing to ship with bugs unless they kill somebody. And even if you don't know, then you ship it anyway, right? You shouldn't, but that's what you do. And I believe that language could help a lot, because what we are missing are abstractions that conquer this complexity. And I, as a language researcher, of course, firmly believe that languages, entire programming languages, are the abstraction that will help you conquer software complexity. Not algorithmic complexity, real complexity, right? And of course, these things that we have lying around called libraries, we've had them for 60 years. And then we put APIs on them because API is a nicer slogan. It sounds more American, right? So, hey, great abbreviation. But then we realized we needed frameworks. And you're using frameworks all the time. And behind every framework, as Guy Steele and others have said, there is a language trying to get out to protect syntactic ideas, then semantic ones, and then support the logical ideas that you have. Because that's what languages do. Okay. Let me give you a very concrete demo. How many of you develop in JavaScript? You're all liars. Because you don't develop in JavaScript. What you actually develop in is Angular, React. Oops, sorry. It's hanging here. Oh, my talk froze. Apologies. You develop in a whole bunch of frameworks, and they're actually little programming languages, because they're not JavaScript. You really have to know more how these features connect. And what you see then is that you are forced by your employer, who chose the language for you, to program in a language, but for each aspect of your problem area, of your software development problem area, you pick the right language. Okay? So a trend that I see, and I would love to see a lot more of that, is that we develop tools for conquering complexity. We started with spaghetti programming. We went on to structured programming. Structured programming was eventually replaced by object-oriented programming, and some of you are still suffering from it. Right? And what I'm hoping to see, and what I actually do see, especially in the JavaScript world, in the Ruby world, and other scripting language worlds, is that we go to a world of language-oriented programming. And in this world, what you will do is you will formulate the solutions to software development problems in the language that is most appropriate and brings across the intent so that people can read the software in 10 or 20 years. Or you can read it in 6 months and not hate yourself. Right? And if needed, you will make your own language in an afternoon. And then you will grow it into a robust product. And you link all these solutions in different languages in one host language together, and that is a software system. So that's language-oriented programming in a nutshell. And what I want to start with for the next 10 minutes, I want to give you an overview of a case study we conducted and published at ICFP 2 years ago. So this is Benji. See you around? Oh, he left. That's too bad. Okay, so Benji is responsible for the video production at Lambda World. He's the overseer. That's what I'm told. So what does that mean? I produce slides. You are making videos. Somebody's recording the audio. When they put it out there on the web, what they want to do is they want to do a prelude, so it says Lambda World and all the sponsors, and more money comes in for 2020. And then you have a postlude, and it says more Lambda World. And the way you do that in this world, you use what's called a non-linear video editor. And you click and clack on your mouse, and you strike your keys, gently go over them, and stuff pops up, and then a video is produced. One video after a lot of work, right? Of course, Bench is not doing one video. I overcounted. When we did RacketCon, we did 25 of them. So around here, you do this a lot. You do a lot of that, right? So you are all hobby language developers. That's why you're here, right? Deep down. So if you were Benji, what would you do? And of course, you would tell me that you're going to develop you're going to use a scripting language for one of those non-linear video editors. Well, sadly, these things are really, really bad things. You can't use them. As a programmer, you don't want to use them. So, of course, what you do is you say, hey, I'm a hobby programming language person. So I am going to, of course, make a programming language. Okay? So we're going to make a video programming language for scripting these nonlinear video editors, so that Benji has a very easy time getting it done. Come on. So the first thing we do is we need a language of laying out video clips, preludes, audio clips, PDF slides, and merging them together in the right way. That's the surface language in which you will script these video scripts, right? And that's relatively easy to do. As a functional programmer, you know you need define, you need lists of clips, you need appending of clips, you need some filtering of clips. That's not bad. But, of course, you really want to render this, and you want to render it as you go, so that you can experiment with it and see what actually happens when you do the final production. What that means is you have to map these data structures that this programming language produces into the renderings, into the renderer's FFI. And what you will see very quickly is that you have repeated mappings of data structures to bit vectors. And the syntactic patterns are repeated all the time. Of course, what we do is we make a programming language to make that easier. So the first little DSL is the green one, and then we use a DSL to write a single program. We make a DSL to write a single program so that we can express very clearly how to render this on the back end. And we can actually, of course, replace the back end by changing the DSL, not the program necessarily, right? Well, you're probably here because you love types. I don't. But I have to program with them sometimes, like now. And so, of course, you want type video. For example, you want a refinement type system so that you don't over-index into a videos playlist. You may want to insert certain advertising slides, sneak in some promotion for your promoters here, right? For your supporters, and the right playlist. And you want your type system to verify that this is correct before you render it, because it's expensive to render. Of course, we make a type system, and deep down in your heart, all of you want to be type system designers. So, whoops, I lost my connection. That's just really bad. Okay. So what you get is typing rules. Okay. What are typing rules? Anybody? Typing rules are the language that type system designers have defined, have developed over 35 years, 40 years, to do with you what you do as a type system designer. You write down horizontal rules. Greek letters on top, Greek letters on bottom, pluses and minuses, and everything is fine, right? How would you express this so that you can generate from the green bubble, this blue bubble, a typed video language? What would you do as a hobby programming language designer? Of course, you would develop a programming language in which you write down typing rules just like you would write them down in a paper. You click a button and out pops a DSL. You heard that right. We made a DSL to make a DSL. Right? That's only the first step in the chain. All right. So what we have now is we have the green DSL, from which we started. We compile with a video FFI DSL to the renderer, which is not a DSL, that's why it's red. We have a DSL for writing down typing rules to generate a typed DSL, so that DSL is all over. What would you do as a hobby language designer if you see that you're doing a repeated task that is syntax-oriented? Of course, you would make a DSL for making DSLs that make DSLs. Let me repeat this. We made a DSL so that we can make the turnstile DSL, which captures the type discipline, so that we can generate DSLs such as type video. That's where productivity comes from. And that's where clarity of expression comes from. When you read those typing rules, you know what's going on. All right? So all of this sits on top of Racket, and we call this language-oriented programming in Racket, because that's what we support. So everything is eventually reduced down to this blue thing down here, this Racket thingy, and all these languages work together. The values that they generate work together, and in this case, work together very properly. You are developers, you know that a language comes with an IDE. So clearly what we want to do is, we want to take an IDE like Dr. Racket and automatically specialize it to the DSL that you're in. The automatically was a lie. But it's almost automatic in some cases. So what you say up there is you want an IDE for the video language. The IDE, of course, needs to come with a preview button so that the embedded video clips that you have here can be played as we edit the program. Believe it or not, inside these video clips, you have code. Because you must be able to abstract over a particular position in the prologue and splice things in. So you clearly want variables sit at certain slides. Of course, you also want videos inside of the expressions that are inside of videos. And we can do that. Turtles all the way down. You know what that is, right? Okay. This is all there is to what Benji has to do for one video produced here. That's what we did for RacketCon. Okay. And if you want to produce all of them, what you do is use map, your friendly iteration in functional programming languages. Right? And then you have all of that. And here's how the productivity works out. The person who drove this effort is Leif Anderson. Leif was responsible for doing the videos at RacketCon 2015. Leif edited every single video with mouse clicks. It was a pain, and you know where it was. In 2016, Leif developed this video language, not the type part initially, and redid the videos for 2016, developing the programming languages, these 4 DSLs, and running the video channel for YouTube took less time than in 2015. That's productivity. So we are in the business of programming languages. Do you understand that I didn't pronounce it the normal way? Okay, good. So, what does language-oriented programming take? Clearly, we must be able to create DSLs on the fly. They're not necessarily robust, but we can harden them later on. If we're on the right track, we can figure out how to make them better. We must be able to program in the same DSL without leaving our IDE. And a change to the DSL must immediately be reflected in the program that we're writing in this DSL. Okay? That's the first two bullets. Hypercritical. If you don't have that, you don't actually have language-oriented programming. You have something else. Then you compile it all down to this wonderful, amazing host language, and you connect these programs, and they're usually smoothly connected until you have hiccups. And that's when research comes in, because these connections aren't always safe and secure. So honestly, I would love to sell you a bridge in New York or paradise on Earth, but I'm an honest researcher. I will tell you that disadvantages and downsides, and there's still work to be done, which is why I'm not finished. But OOP was sold way before it was ready for industry, so I'm selling the LOP too. All right, so that's what we're going to focus on for the rest of the talk. And I'm going to show you a little bit what this looks like in a typical Racket module. A module starts out with a declaration of which language you are in. So #lang, and then you need to write down the name of a programming language. And there are little tricks to make files into programming languages, so you don't have to have a name necessarily. The next thing you do is you define compile time functions as if you are defining functions. So they live at the same level. Functions, compile time functions, same level. We'll look more at that later. What you do with these things, you export them. You can export functions, constants, classes, objects, and syntactic constructs. So languages clearly become something like libraries in your world. Right? Best of all, on the way out, as you're providing a feature, you can say, here's the new name, here's the old name, in the next one, use this thing over there. Use this old name instead of the new name. And that's an amazingly powerful trick. Okay? So what I'd like to show you for a moment is what this, something fell, whatever, what this looks like in Dr. Racket. Can you see this in the back? Should I make it bigger? Okay, good. That's the program, #lang Racket. I'm in the Racket programming language. The next thing is a function definition, simple recursive stuff, kind of what Harold showed you. How many elements to sum to the threshold th in this list, starting with a count 1, running sum is 0. Here's some unit tests. Okay? Unit tests are in a submodule called module plus test, and when you run that, you actually get that some tests pass and some tests fail. 1 divided by 0 in this list, it fails. Okay? But all the other tests passed, so we're okay, kind of. So let's play this again, right? So that's what a module looks like. And while you run it. Here is how you turn a module, a plain old module in your software system, into a programming language. You export one identifier, #module begin. I know, it's a weird name. We have more weird names, you'll see. Where does it come from? This is the entire module. Where does it come from? Well, that language thingy, of course, is the first import, the first require into our module. So this name is bound somewhere in the definition of this language thingy. So this goes all the way down to a language called kernel, which is more or less a VM-like programming language, virtual machine language. Okay, so then this is how you make a new language. You have a base language, this red thing at the top, and that's where you start from. That's the old language. And then you subtract some features that you don't like. I don't like add. I don't like addition. I will never give you addition again. How do I do that? I just don't provide it, right? That's easy. I define new compiler hooks. I put new functions into the compiler. And the compiler recognizes this name and says, oh, I'm going to use this function to deal with this kind of thing. Okay? Best of all, I can reinterpret an existing construct in the base language with new meaning. And that's an amazingly powerful thing. And that makes languages really, really cool. So the new language is kind of like the old one, but and you enumerate the differences. That's one way of being very productive with making little languages. There are other ways, but that's for some other talk. What do you reinterpret? Of course, I just said you reinterpret addition. I hate addition. It should be subtraction. It should have been subtraction from the beginning. Adam and Eve made a mistake. So that's easy. That's the visible stuff. But there are invisible points in your programming language. And those are the ones we really, really want to redefine very often. So for example, there's something called #app. And then this is #module begin thingy. So we'll talk about this very, very quickly and see what they do. When you see a function application which is written in this beautiful way with left parenthesis, expression for the function, expression for a bunch of arguments, close paren, right? That is parsed into a parse hook, #app. And that's just another feature, and just another syntactic construct. You don't write it down. You could if you want to. Doesn't make it any difference. But it's much more convenient not to write it down, because we insert it for you. And then if the compiler has a way of doing something with it, it does something with it. And if it doesn't, it doesn't. Usually it does. Like in Racket, it does. It's a functional application. Here's another one. When you write down #lang language, bunch of stuff, then what really happens is we encapsulate all these blue thingies into left paren #module begin thing, close paren. And this is how you can start rewriting the entire module. Which is, for example, you can gather the types that you find in there and use the types for type checking, mutual recursive type checking. You can gather the definitions and movements are in place, and other things. We will use this trick to build a truly lazy language in 15 seconds. This is it. This is the entire lazy programming language. It grabs, it puts into a compiler a feature called very lazy language. It consumes the syntax tree, this blue thing, these blue thingies. It doesn't do anything with them. See that? It generates code. That is generate code. That's a long way of saying it, but we call it #quote. And it uses module begin. Look at the color, it's red, right? To generate a single function call. Display this little thing, this little list. Okay? So we generate code here, and we use the module begin that comes from Racket. And then we export this very lazy language thingy as the blue module begin, and we will use it in a blue module. Let me show you how that works. Come on. So you are in your programming language here, Racket. We will delete Racket, write S expression, that's for mixing in modules as thing. You can see it goes blue again, that means it found its language. We run that, and that's the result of the program. No more errors. Well, let's see. Let me pick up this name here. Maybe we can run something here. We run it on, come on here. Let's run on the empty list. Let's see what happens. 20 and 10 in the empty list. Well, that's a really lazy thing. Okay? And the language is really this thing. It's not quite true. over lunch, as I was waiting for my lunch out there, I was actually adding this feature here, how to interact with the REPL in the bottom, because I also want to adjust the IDE to deal with this stuff, right? So this is the phrases that you saw. I said I was lazy. What do you not understand about I'm lazy, right? That's where it comes from. Over lunch. Actually, just waiting for this lunch to come out. That was it. Well, that's very lazy. That's maybe a bit more lazy than you imagined. But that's honestly how a lazy language should really work. Denotationally, that's actually how it works. Most people just don't, most programming language people don't do that. So let's go back to producing a really good lazy programming language. Because very, very lazy is not very, very interesting. So we'll need 15 minutes for that, and I have about 15 minutes left, so it's just in time, right? This is the program that we're looking at. How many elements to sum to threshold, right? And we go through the empty list case. We say the first is 1. We add up the sum, 1 in the running sum. If it's greater than the threshold, we return the count. Otherwise, recur. Not recurse. That's cursing. We just recur. That's English, right? Okay. So here's an element. Here's how you do that. Okay. And then, of course, you can also get this divided by 0. Because it's a strict programming language. It evaluates the list. And the last thing says divide by 0. So clearly you want to get an error. That's where the error came from. And divide by 0 could, for example, stand for this is a list of 1 billion elements. And I don't want to suck all 1 billion elements into my programming language, in my running program. I want to lazily create this list. Right? That's why I may want a lazy version of Racket for just this processing that list, that kind of list. Okay? So that's what we do. And the way we do it, we mix in this programming language called Lazy Racket, which I'm going to make with you in a moment. This is the beginning. I must make a language that means I have to provide from this module this funny name called #module begin. Now I'll use the red one. It's boring. Then I'm going to import the programming language for making DSLs. It's called syntax. It's in a place called syntax/parse. Okay. The next thing is I finally define a new syntactic construct, lazy function application. Okay. What does lazy function application do? Well, it uses something that's pattern matching code as opposed to pattern matching algebraic patterns, which of course we also have as a library defined as a syntactic construct. So you have this thing that matches code. In this case, what it matches is, of course, #app fx1 to xn. But it's not really #, it's an underline. And that underline plays a role. It says, whatever name this feature has in the module where you're going to parse it. Okay? And that's the trick. So now we can generate a function application with a red #app, the one that comes from the strict world, but we lambda wrap every argument that goes into the function. Okay? So clearly now every function argument is delayed in a lambda. All right? And then what we do is we rename this feature lazy function application to #app on the way out. It's blue now. See blue and red? All right. Good. What happens when we move this, when we put this lazy Racket thingy into a module that has just this little expression, 42 plus 1 divided by 0? Well, the parser inserts this #app. And it comes from there right through this import. Now, whoops, I went one too fast. Okay, so now you take this thing again, this blue #app, and a red #app pops out. Why? Because blue #app is lazy function application, which rewrites these expressions, 42 and 1 divided by 0, into plus lambda nil 42, lambda nil 1 divided by 0. And of course, now you see the problem. When Rackets plus receives a lambda nil, it will do bad things. It will spill your blood. That's why it's red. That's what I tell my students. They're terrified of errors afterwards. So clearly what we want to do is we want to strictify plus. And we need to strictify all other functions that are strict in the Racket sense, and I need to be strict in a lazy language, because lazy languages only undo this delay when they hit a strictness point inside their programs. And we define the strictness points. Okay? Here's the strictness point, plus. Here's another one, incrementing the counter. Add 1 to the counter. I prefer add 1 because it signals a really clear intention. This is a counter, right? So what do? Well, what I do is I write a function called force. Because thunking can happen repeatedly. I haven't optimized anything yet. I could very easily, I don't. I do a function force star, which says if you are thunk, which is a wrapped, it's really a wrapped lambda, thunked lambda, I'm going to apply you. And I'm going to force you again, just in case you were wrapped multiple times. But if you're not a thunk, then I know that you're a proper value, and I can deal with you. You're now a Racket value, a plain Racket value, and my plain Racket strictified functions can deal with you. Okay. And then I define strictify, and strictify is, of course, a function that is curried, takes the function name, a bunch of arguments, and then maps force over all the arguments, reducing the delay and evaluating them now. Okay. All right. Now I can define at1, strictify of plain at1, I call it at1s. I define plus dash s, strictified plus, and I provide each function as I define it. And I put the provide right next to define so that I see what I'm getting out of this module at this place here. That's not what I normally do. What do you see here? You are observant developers. You are seeing a syntactic pattern. I'm repeating this right here. What do you do when you see a syntactic pattern? Dry? Something like that, right? You have these slogans lying around in the development world. You abstract of it. You don't ever repeat yourself. Ever. That's what a good programmer does. And that syntactic pattern, therefore, must go away. Here's how it goes away. What we make is a compile time function. We won't export that one because we don't need it. Provide strictified. And provide strictified, of course, is just the normal thing, matches the syntax. And it defines a name strict, strictified, the name that came into the macro. Name strict did not come in. And then we export that name strict as the name. Just like the syntactic pattern. And you should be worried as hell that name strict is used here in this line, because that's where we use the macro right away, and in this line. Unfortunately, we developed something called hygienic macro expansion 35 years ago, and good macro languages have this by default. So we have it, of course. But what you also see is you want to export a whole string, a whole list of names that are strictified. So clearly you want another macro that takes a whole bunch of identifiers and then unfolds into this macro over here. And now exporting a whole bunch of functions that are strictified takes one line. Once again, by just stopping and observing for one moment that you have a repeated pattern in your program, abstract over it, you save yourself a lot of work. That is true for spreadsheet programming, JavaScript, and syntax. Here's our module again. Now, I have one more thing to think about. I thought about all these functions up there in the big box, but there's a function down here. A function that says, give me as many elements as you want, and I make a list. That thing. Here's how you write that. You don't strictify. You don't strictify. You redefine list and make it a different function. List.r means give me as many arguments as you want. And it turns out they come in as a Racket list here. Doesn't matter. We're just going to return them. Why is it okay? What happens when we apply list? Every single argument is delayed. So what we're returning is a list of delayed arguments. That's all there is to it. Okay? 2 lines. Strictified, not strictified, sorry, lazyfied list. Okay. So we've programmed for 11 minutes. That means I have 3 minutes left to show you how it actually works. Okay. That's what programming languages means. So let me show you how it works. We are going to look at buffer 2. This is the lazy language. In addition to a bunch of functions I showed you, I export if, cont, else, let. If I mouse over them, you can see can you see the arrows? Okay. You can see that so my IDE tells me where the scope is for this thing. So cont is imported from Racket and is exported into my lazy language. Works just fine, because there's nothing lazy or strict about this thing. Same for let, your usual let from a functional programming language. You define recursive function definitions. We also export and import submodule constructors. They're called module plus, little submodule, requiring into things. And here's the rename out. Lazy function application becomes #%app. That's the critical thing. We turn function application into a lazy thing. So that's the whole function. It's 62 lines. We go back to our buffer 1, and we change, we delete very dash, and we have a new programming language for this module. Whoop, it fails. Let me show you what fails. You can actually see from the last blue line what fails. Why does this test case fail? What do you think happens? It's a function application of a unit tester. It's assert. Right? Assert how many elements to sum 10, list 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it wants to know that 5 elements are enough to give you 10. What fails? It's a function application, right? Assert is just a function. It's delayed. It produces a lambda. All these things are lambda, but this doesn't want that. So I could strictify, and there is a version of that. I could strictify check equal, or I can show you how one does that on the fly. What I do is, I'm going to oops, where am I? 2. I'm going to export a function called --bang. I named it in honor of Haskell, because when you program lazily in Haskell, you have to put exclamation marks everywhere. Otherwise, you don't get performance, right? Okay, so --bang is just this thing that says, I may be a thunk, let me force it if you're a thunk, right? So I'm running a thunk. It's basically force star. So if I export that too, and I go here, if I didn't import you, and I will get back to this later, if I didn't export, if I didn't export this, and which one? I think that's it. Oh, there's one more. It's that one. Sorry, I'm going to use cursors. Of course, I also need to do this infinite list thingy. Oh. Where am I? Oh. And now my division 0 goes away, and this thing evaluates to 5, just like it should. 0, 1, 3, 6, 10. 5 elements, I got 10. I have a lazy programming language. 15 minutes. Can you do this in your language? Thank you very much. So here's a bunch of things I didn't show you. I'm not quite done. I have extra time, so I'm going to keep you here. You're not going to be bored, promised. What I didn't show you, there's lots of stuff I didn't show you. For example, I didn't show you that you can define macros that generate macros. Well, I also didn't show you that you can macro-generated macros. Now, don't fall off your chair now. You can actually do macro-defining, macro-generating macros too. That's 3 levels up. There is no limit. There is absolutely no limit. If you were in Lisp or Clojure, you'd be host. What we have done over the last 15 years, we've developed techniques to make sure that these phases do not interfere with each other. You can break that, just like you can break hygiene, for example, but you must be able to clearly think in a stratified manner, if you so desire, and usually you do. Okay? There are other tricks that we do, so macro-defining macros all the way up. So on an LOP, what you have is an entire tower of compilation phases. And each, on one level down, there's a runtime. Okay? So your entire language is available, and you can simply move it up and down the tower by saying require for the compile time, or require for the compile time of the compile time. And boom, you got Racket 2 levels up. You can generate information so that the macros for the next module can pick up compile time information, types, scope, record labels. And this morning you saw a little talk about nim and d and how you can reflect on these things. It's all been there for a long time. Okay? You can define inside of macros your own evaluation. You expand the loop. That means you don't have to have a hashlang DSL. You can integrate the DSL inside of Racket or inside of another DSL or tower of those. And that's an amazing piece of power too. Once you have that, of course, either with the hashlang or the integrated DSL, you can build multi-pass compilers, including optimization passes, which is what a DSL is for. Right? One of the things you want to be able to do is speed up what's going on in this particular little domain. And believe it or not, I can deal with ugly syntax. That's what you call semicolons. So let me show you how semicolons work. Let me just show you a bunch of programming languages. So in reality, lazy doesn't have to be built. We have a hashlang lazy, of course. It's baked into the Racket ecosystem. If you want to use it, you use it for the part that needs to be lazy. It has all the features that you would expect. This is the program we've written. You want types? We have an extremely sophisticated type system. And unlike, for example, recent ML, ours is type sound across the interaction between typed and untyped Racket. I'll get back to that. So one single change in line 1, actually, I have to make this bigger, sorry. One change in line 1 from Racket to type Racket, and uncommenting my comment that I always write down anyway, what the type of the function is, and boom, I have a type program. You want to program in data log? You program in data log. And it doesn't even have parens. That's what I call ugly syntax, or what you guys use. And of course, what we do is we have a little parser that parses these things directly into macro calls, left paren, right paren, and everything works out. It's not 100% true. There's a hiccup between the parser and the macro system. It's one of the things I want to fix one day, or we want to fix one day. I'll probably retire before that. So, on that note, I believe, I have 5 minutes left? No time left? Well, if I have no time left, onwards to LOP. It's an amazing paradise, if you can realize it. The few slides I had left were the problems, but since I don't have time, there are no problems. Thank you very much.